Okay, wonderful to meet all of you. My name is Linda. I'm a pretty mediocre programmer. I'm a children's book author. I'm an illustrator, and I'm a business school dropout. And I'm probably the first children's book author to address this crowd in a long, long, long time. And the reason why 3 of those identities are in parentheses is because I'm still uncertain about them. The only thing I know for sure is that I never graduated from the business school, but I don't know what I will do when I grow up or what my title will be around that time. And I think that's the thing with us humans. Computers are binary. Computers can be one thing or the other. But as humans, we contain multitudes. We can be many things at the same time, and that's what makes us beautiful. So my talk today will handle software and the idea that if our kids grow up in a world where their first foreign languages, in Finland they will be practicing Finnish, Swedish, English, and JavaScript, we need to totally revamp the way we teach software education. Instead of grammar classes, we need to be teaching poetry for our kids. And what I mean with that is in the same way as we don't anticipate kids to learn natural languages by just teaching them grammar. I didn't learn Swedish by doing ja tala, ty tala, hanno, hon tala, or so forth. We need to teach languages by allowing our kids to use them. I learned Finnish by reading books. I learned Finnish by writing poems. I learned Finnish by using the language. And it doesn't just happen by virtue of having kids use computers all day long. We don't think our kids will learn to be citizens of a country or to learn a language by just being surrounded by Finnish or Swedish all day long. We actually need to teach them, and that's the role of us adults in the room. So my journey into the world of software starts from storytelling. I think stories are among the most strong things we have as kids, and they stay with us and shape the way we see the world for years to come. I grew up with role models like Pippi Longstockings and Lilla My, and I think they shaped the way I saw the possibility of the world. And when I started this project, I realized that there are no role models in the world of ICT for little kids. And I was practicing Ruby programming at the time. So it's a programming language, object-oriented programming language. And every time I would run into a problem that I didn't quite understand or a piece of jargon like, what is object-oriented programming or what is garbage collection in iOS, I would try to think about how a 6-year-old little girl would explain this concept. And that's how the character of Ruby was born. She's very fierce, a little red-haired 6-year-old girl. And I think around this time, something in my brain switched irrevocably. So, you know, people who see numbers as colors, I started to see the world of technology full of stories. So all of a sudden, when I thought about it, like, what would Apple, the company, look like as a character? Well, it would absolutely be the snow leopard, who's beautiful and likes well-designed things, but doesn't want to play with the other kids because they are too messy. And then there would be Linux the penguin, who's really, really efficient and smart, but somewhat hard to understand at times. And then there would be the green robots that would have a lot of siblings, and they would be very powerful, but a little bit too messy, and they grow up a little bit too fast to be reliable. And the idealistic Firefox, and so forth and so forth. And I went to my mom with this idea that what if we tell about all of the stories and the values that exist in the technology world? And my mom was, oh, Linda, are you making some sort of a Soviet propaganda children's book? That sounds very 70s for me. And I realized that no, I actually need to do something a little bit bigger and more profound. So the challenge in this endeavor was that I wasn't a very good programmer at this point. I had never written a book before, and I wasn't very good at drawing around this time. This was 3-4 years ago. But if anything, I think programming and learning to program has taught me a lot of resiliency, a lot of persistency, and a lot of the idea that the only way to learn new things is by making a lot of mistakes. And these are some of the very early pictures I made for the book. And you can see they are not very good, but I figured that if I draw 1,000 circles eventually the circles will be better, and I can move on to more advanced things. And I kept drawing and drawing, and I had this wonderful Ruby on Rails community around the world that started to imagine with me what would a world of software imagined by a 6-year-old look like. And I kept drawing, and I got these little plush toys from Belo Horizonte, and I started to sort of have that self-efficacy, that belief that, yeah, maybe I could be a children's book author. And I had a little bit of the idea of teaching programming to kids before syntax. So what are the sort of the underlying principles of computation that all kids should understand even before they learn a specific programming language? And then in 2013, I did the best and the worst thing I've ever done in my life. I put this project on Kickstarter. And around this time, it was still a little bit unclear whether Kickstarter was a really viable platform in Finland, whether it was legal or not. But I figured that if I ask for $10,000 to self-publish a book, it's going to be okay. No one's going to notice. And it went well beyond that. So during the first 24 hours, the campaign gathered $100,000 worth of pre-orders everywhere from the world. And during the 30 days that it was online and available, the book gathered $380,000 worth of pre-orders from Amman to Australia, from Belo Horizonte to Berlin. And all of a sudden, I was a children's book author, and I was a person who did a book on technology education. The only problem was that I still didn't have the book at this point. I had an idea, and I had a really convincing video, but no book in hand. This was also 20% of the annual book exports of the entire country of Finland. And I was a first-time author, and I panicked, and I cried. And now, 2 years later, I can finally sigh of relief and say that I have an idea of what I'm doing right now. But it's been an interesting and pretty incredible journey. So Hello Ruby has been published in over 20 languages, among them Swedish. And I'm working on the second book that handles, or the second book is out that handles how computers work, and I'm working on the third book of how internet works. And the more I've worked in this field, the more I've realized that we need radically different ways of engaging people from outside of our little bubble of technology-oriented people to make this field approachable and fun and exciting for all types of people. And the demand for material like this is there. That's just proof of the book being published in so many languages already. And one of the bigger surprises for me has also been the fact that teachers around the world have embraced these materials. They've sent me lesson plans from Jerusalem and exercises from Taiwan, and really wanted to sort of raise a generation of kids that is more diverse and embraces technology as a medium of creation. So when I talk about coding and technology, I don't talk about ICT, I don't talk about e-skills, I don't talk about digital literacy, I talk about coding. And I think this is one of the big problems for us as an industry. For people who are so obsessed with exact words and exact expressions, we are pretty loose when it comes to talking about technology education. So what I want to talk about you today about is programming and coding in particular. And I want to talk about programming from the perspective of a little girl. And you've met her a few times already. Her name is Ruby. She's 6 years old, completely fearless, a little bit bossy, very imaginative. And when Ruby's father comes home and says, "Oh, Ruby, you need to dress up really quickly. We're running late from school," Ruby does dress up, but she leaves her pajamas on because Dad didn't specifically tell her to take the pajamas off. And when Ruby's dad comes to Ruby's room and says, "Oh, Ruby, your room is a mess. Clean up all the toys." Ruby, she cleans up all the toys, but she puts and leaves the pens and papers on the floor because Dad, pens and papers are not really toys. And I think all of you who have little kids know this very obnoxious gene that is there. But the kids also learn something very profound about how to speak to a machine. Namely, you need to give very exact commands. You need to give them in the right order. You need to be very careful when naming things. And instructions should cover all types of scenarios and be modifiable. And most importantly, I think even the biggest problems in the world are just tiny problems stuck together. That's the one thing I'm very, very jealous about for people with an engineering discipline. You have this mentality of being able to fix problems and solve them by breaking them into smaller pieces. And turns out kids around the world, they have this aptitude and they have this skill to embrace technology and problem solving in a way that we parents can't even foresee in advance. But it all starts from having the correct vocabulary and coming up with more diverse ways of engaging and showing pathways and role models for these kids. So the word I found that sort of describes what I'm trying to do here is called computational thinking, and it's not thinking like a computer. It's a human skill that means breaking down a problem in a way that allows a computer to effectively carry out the task. And when I talk to laymen about programming, I try to explain to them that actually programming consists of 3 separate parts. It consists of planning the program that you're doing. It consists of writing the program into a programming language, into code in a programming language with the correct syntax. And then finally, it includes testing and debugging the problem. And only step 2 requires coding skills. Only step 2 requires the actual act of writing the code. Number 1 and number 3 are very humane activities that include a lot of resiliency, problem-solving skills, decomposition skills, and so forth and so forth. And when we think about programming, we think about ones and zeros in a row. And when some of you think about programming, you think of the assembly code that was written in the 70s and 80s. But luckily, like the world of programming has advanced quite a bit. There's layers of abstraction that have been written on top of each other so that modern programming looks like the code example on the left. So both of these examples produce the exact same output. They write hello Ruby, but there's been thousands and thousands of man hours in between to make it a little bit more simple and understandable. And when we look at different kinds of programming languages, we can see that they all look a little bit different. All of these programs output the number 2, so they count how many fruit Ruby has in her bag. They all look a little bit different, but you can kind of see that there's similarities in each of them, and you can see that they all utilize the same thinking structures. So what are these thinking structures? Well, when we think about computational thinking, we think about concepts like logical and critical thinking, like algorithms, like pattern recognition skills. And I remind you that none of these is actually like a programming language per se. All of these are the higher level thinking skills that are required by humans in order to translate things to into a code that machine can understand. But more importantly, computational thinking encompasses also practices. And those practices are things like persistency, tinkering, creativity, working together with one another. And I think it's vitally important that we teach both of these things, that we encompass all of the different aspects of computational thinking. So I'm going to show a few examples of the ways that learning to program is actually learning to think. It doesn't require you to only learn about the grammar, the syntax of coding, but it's a thinking skill. So decomposition, every single programmer in the world starts by decomposing the problem. And for your little kid who wants to be a games programmer when he or she grows up, they need to break down the game first. They need to realize who's the hero and what are the items that they are collecting. When does the time run out? They need to learn the art of decomposing a problem. The other thing, pattern recognition. Being able to spot patterns and see how they interact with one another. Here's a few of Ruby's friends, and it looks like the android has done something or forgotten one step in his algorithm, and the fox has done something in the wrong order, and there seems to be something a little bit funky in the way Ruby wrote her loop over there. By the way, all of you who've done flowcharts in your educational systems in the 70s and 80s, I'm so jealous for you. It really teaches you how to think for a problem. Let's reintroduce flowcharts to schools, please. And then algorithmic thinking. So for some reason, parents, they like panic when they hear the word algorithm. It sounds like a scary big Facebook word. But for kids, algorithm is such a wonderful and exciting word. And we talk about algorithms and really realize that a cupcake recipe is an algorithm. Because after all, algorithm is just a step-by-step solution to solving a problem. And if you have a really good cupcake recipe, you can switch the amounts of ingredients you have to make different kinds and amounts of cupcakes. And that's what an algorithm in the end is. And then finally, abstraction. The idea that a computer programmer or any person needs to be able to move along abstraction layers comes down to working with kids in the way that we talk about cats, and we talk about cats that have different kinds of tails. All cats have a tail, but they might be different kind. All cats have fur, but it might be different colors. All cats have eyes, but they might be different colored, and so forth and so forth. And some of you now in the audience are like, aren't we practicing these things in school already? Aren't these things that kids are anyway learning in their lives? And you're hitting the point exactly. These are skills that any person needs to survive in the modern world, but we just haven't made the jump into showing to teachers and regular educators that you're actually already teaching these skills. Now let's just help you see these things through the lens of a computer. So in order to engage a more diverse audience of kids and adults to get excited about technology, we need to come up with a different way of teaching people. One of the things I ask is, how does a loop feel? So in Ruby's world, we practice the concept of a loop, the idea that a computer is really good at repeating steps over and over again, endlessly, by doing a dance party. And Ruby's favorite dance move, it goes like this. She likes doing clap, clap, stomp, stomp, clap, clap, and jump. And with the kids, we practice a for loop by repeating this loop 5 times. And we practice a while loop by repeating this loop while I'm standing on one leg. And then finally, we practice as a homework an until loop by repeating this dance sequence until mom gets really, really frustrated. And this way, we move across the abstraction layer by having first physical experience what a loop feels like. Then we maybe practice in Scratch, a visual programming language. Then we write the thing in code, whatever the programming language ends up being. And then we observe outside and see that actually, if you have a thermometer, it has some sort of a loop written inside of it that every hour it checks if the level of warm is the same as before. And if it's not, it changes accordingly. Or that games have all sorts of loops inside of them, like keep moving the hero until it hits the enemy, and that a website has a for loop inside of it. It allows you, when you sign into a website, it might have a loop that asks you 3 times for your password, and if you don't remember the password, it locks you up, and so forth. So kind of coming up with more diverse ways of teaching concepts that are foundational and underlying behind computing. Well, why is this important? Just for the reason that you all are here today. The world is becoming more and more run by software, and the people who understand what humans are good at and what computers are good at are starting to have more and more power. And honestly, I don't want a world where only the young, white, 20-something-year-old boys at Facebook and Google get to decide what kind of a world we're building and what kind of problems matter and what kind of things should be moved forward. I want to see problems and solutions by all types of people, and I want to give people that power to build those solutions. And when we think about software, especially where I come from, in Finland, it's still considered, like software is Rovio, software is Supercell, software is games, that's what it is. But all big changes in the world start out looking like toys. And software is definitely not only games, it's city planning, it's neurosciences. We couldn't do the stuff we do today without the ability to simulate and automate things with computers. It's music. Here in Spotify, here in Sweden, you used to have CDs, now you have Spotify. One field by one, software is taking over the world. And the more I think about my work, it's not only about teaching kids the rote skill of programming, it's preparing kids for a world where every problem is a computer problem. And that's a pretty big and bold statement, but I believe that in order for us to solve the really bad and big and hairy problems of the world, like hunger and education and energy, We need to use the persistency of computers and the creativity of humans in order to really solve those fields. And one of the things I think our industry has problems with is showing the joy of technology. And for me, I see that there's two types of joy in programming. There's the first type of joy that maybe many of you recognize in the room. It's the joy when you write a beautiful, abstract a beautiful function call, or you write a program that calculates the square roots of the first 20 prime numbers. And that's one type of joy of programming. And that's what school excels at, and that's what educational systems are really good at promoting. But then there's the second type of joy in programming. It's the type of joy when you have a problem and then you go online and then you copy-paste snippets of code and you put them together with duct tape and you're almost scared of pressing the compile button to see if the problem or the program works. And oh boy, it works and I made this happen and the computer obeys my will. And I think that's called play and that's called joy. And that's what we're missing oftentimes in our education. When laymen look at programmers or people who work in technology, they don't see the highs, they don't see the lows, they just see the programmer in front of the computer. When we look at a sportsman, we can see that they are jumping and they are running and they are the emotions that happen inside of the art or the practice. We don't see that in the technology field, and I think it's up to us to make it visible. And this isn't a new idea. Seymour Papert, who's the apprentice of Jean Piaget, a very famous pedagogician, his big idea in thinking was that programming is a thinking tool. It's a way of establishing intimate connection with some of the deepest ideas in our world. That learning to code teaches you simulate your ideas. It teaches you to model your ideas. It can be used in math and arts and across different disciplines. And when I really think about it, it boils down to play, and it boils down to finding the joy of programming and technology for all types of learners. And when I think about who understands play best in the world, we don't need to go far. We need to go all the way to Denmark and ask the people at Lego who have this profound 40-year-old experience of what it means to teach play. And I asked Lego people, how do you define play? And they gave me this 5-step definition of what play includes, and it has things like physical play and symbolic play, and only the 5th one, and one of them is games with rules. And when we, as technologicians, as programmers, think about how to teach and show the joy of technology, we shouldn't only think about games with rules. And then they give me another chart that has different motivations for play. So there's achievement-based motivation, there's social motivation, and there's immersion motivation. But then for some reason, whenever we want to encourage or help someone get excited about technology, we only use this one aspect of play. We have things like gamification and power and progress and numbers and optimization and provocation and challenging others. Whereas anyone here who has ever programmed knows that there's so much more. There's helping each other, there's receiving and giving support, there's collaboration, there's things like exploration, the joy of finding a new way of solving a problem, and at least for me, the escape from real-world problems. And I think we should be using all different aspects of play in order to make technology as a field more approachable and fun. So when I work with kids, we oftentimes start by building a computer out of paper, real paper. And it starts with the idea that, again, the people here in the rooms who were engaged with technology in the 70s, you could actually touch a transistor. And that's amazing. My generation, the pinpoint of a pen has 300 million transistors already, and no one can anymore touch a transistor. And as a result, we have these beautiful machines that fit into our pockets. Modern phones have more capacity than the computer that mankind used to go to the moon in the 60s and 70s. But as a result, we don't understand anymore how computers work. We don't have ideas about the abstraction layers beneath. And we can't touch a transistor anymore. So with the kids, we actually build a paper computer, we put in the CPU that is very bossy and gives commands to everyone else, and we get to know the RAM and the ROM that help the CPU remember things, and the hard drive, and the GPU is in charge of drawing on the screen, and then the kids get to design their first applications. And one of my favorite stories here is this little boy whose favorite thing in the world was to be an astronaut. And the little boy has these big headphones on, and he's completely immersed with his paper computer. Because you see, he's built an intergalactic planetary navigation application. And the boy's father, who's on the other side of the room, but really far away in the Martian orbit, is the lone astronaut. And the little boy's role is to bring the father safely back home to Earth. And giving these kinds of experiences for kids at their early age of what technology can do and what we can imagine with technology is, I think, the key to raising the next generation of creators. And the funny thing is that computers are not anymore only those little boxes or the phones or these understandable, well-defined things. When I work with kids, the second exercise we oftentimes do is I show them these 4 pictures. I show them a picture of a car, I show them a picture of a toilet, I show them a picture of a grocery store, and I show them a picture of a dog. And I ask the 6 to 9-year-old kids, which one of these do you think is a computer? And all of the kids look at me like I'm stupid, and they say, Linda, none of those is a computer. Are you completely out of your mind? The computer is the glowing box in front of which my mom or dad spends way too much time. But then we talk, and we realize that actually a car is a computer because a car has a navigation system. And grocery stores, they have all types of computers. They have the teller's machine, and they have the ice cream box that keeps the ice cream cold, and they have a burglar alarm. And that dogs, they might not be computers, but a dog's collar might have a computer inside of it. That might be a smart thing if the dog is prone to running away. And I advise caution with the last one. I tell kids that in Japan, toilets are computers, and there's even hackers who hack them. And this makes me the most popular person in the room among the 6-year-olds for the rest of the day, and we don't get any more work done. And we discover that there's actually hundreds of computers in every single kid's home, not the glowing box only. And that this generation of kids is going to be the last generation who remembers the computer as the glowing box by its screen, because they are going to grow up in a world where their teddy bear is a computer and their toothbrush is a computer, and it's up to them to design that world. And the last exercise we do is I give them these little stickers with an on-off button on them, and I tell them that, kids, for this afternoon alone, you have this magical ability to make anything in this room into a computer. And again, the kids object. They go, Linda, that's too hard. I don't know the right answer for this question. And I tell them that neither does your parent. They've just heard about this thing called the Internet of Things or the IoT. But it's kind of up to you to design that world and imagine what it will look like. So my favorite story is this little girl who comes to me with a bicycle lamp, and she's made it into a computer by putting an on-off button on it, and she comes to me and says, Linda, if this bicycle lamp were a computer, I could go on a biking trip with my father. And we could sleep in a tent, and this bicycle lamp could also be a movie projector. And that's the moment I'm looking for. Not the moment when the kid understands the difference between arrays and hashes in Ruby. Not the moment when they understand how to write an if-else statement in JavaScript. The moment when they understand 3 very profound things that as adults even have a hard time understanding. First of them is technology is a wonderful way to change the world because it scales and it creates wealth around the world. And I think us Nordic countries, we understand this very, very well. The second thing she understood was that the world is not ready yet. There are so many things that haven't been imagined or designed or problems that haven't been solved, and the bicycle lamp movie projector might not be the most important one of them, but it still doesn't exist out there. And the third thing she realized was that she herself can be a part of that change. Odds are that she's not going to be the next Steve Wozniak or the big hardware hacker, but for a moment there she felt that she could be the first movie projector bicycle lamp inventor. And I think that's what we should be shielding in childhood and a little bit in ourselves as well. I think the more complex the world becomes and the more we have computers around us, the more important it becomes to give kids a very robust idea of a notional machine. Help kids understand what computers are good at and what humans are good at. And it's not an easy task because computers are becoming more complex and they're getting better at mimicking the way people and humans behave. And it's very funny when we talk about computers. Still to date, when I'm asked to explain what a computer is, I go all the way back to 1945, 70 years ago, when computers looked radically different than what they do today. They were bigger than this room. Now they fit into our pockets. But still, I would explain what a computer is by the von Neumann machine principle. And it goes like this. Computer is any machine where you put in data, you do something with the data, and out comes the modified data. And that is true whether you're liking something on Facebook. Facebook server gets input data that add one more count to the like buttons. Whether you're sitting in a car and you've forgotten to put your seatbelt on, there's input data that the seatbelt is unlocked and there's a pressure sensor that realizes that someone is not sitting here and outputs the beep, beep, beep noise of the car. So input, process, output. And the thing that makes a computer so magical is the memory. Because a tractor can only be a tractor. A pinball machine can only be a pinball machine. But computers can be anything based on the instructions you give to them. And the instructions are called software. With kids, they usually want to play this out, so we make this like gigantic little cardboard box, and I ask the kids to crawl inside of it. Some of them are the input data. There's a little bit of a code snippet, like come out jumping on one leg or come out crawling the other way around. They are the output data, and this is a very, very fast computer, so the kids go round and around and around until the computer eventually breaks down. I think the beauty of computers are that they are these gigantic abstraction machines, and when we think about it, it's one of the most beautiful things humankind has ever done. The fact that we've made electricity first into logic, into bits and logic gates, then it makes a twist again and turns into hardware, transistors and resistors and CPUs and different kinds of components. Then another twist and it turns into software, the apps and the things that we use every single day. And it's one of the most complex and beautiful journeys humankind has ever made. Finally, I think in a world where computers are taking away a lot of the redundant work we have, it's more and more important to teach kids what computers are good at and what humans are good at. With kids, we have this exercise where I give them a big piece of paper, and each of the kid gets a piece of an algorithm. One kid's algorithm might be to make dots. The other kid's algorithm might be to make a circle around the dots. And I put on the computer, and the kids start to go around and around the big piece of paper. And finally, we produce this wonderful, beautiful piece of art, and we look at it, and I ask the kids, if the computer was given the exact same instructions, how many artworks do you think it could make in 20 minutes? And the kids think, and they go like, I think it could make 3 of these in 20 minutes. And I tell them that, like if a computer were given the exact same instructions, it could probably do 100 million of these in a nanosecond, because that's how fast computers are with things that, like, with existing instructions. But then, you kids, you have the power to give opinions of the artwork. You can say that this artwork makes me feel busy or restless or excited, and a computer will never be able to do that. A computer will never have emotions. It can mimic emotions and it can be programmed to recognize emotions to some extent, but it can never have emotions of its own. And another exercise we do is I give kids a Barbie doll, a guinea pig, and a Furby. And those of you who don't have little kids, Furby is the little like fluffy robot that kids nowadays has as dolls. And I ask them to hang each of these head upside down as long as they feel comfortable. And with the Barbie doll, kids can do it for a long time. They can hang it head upside down and throw it around. It doesn't have emotions, doesn't have feelings. A live, real guinea pig, none of the kids would hang head upside down because it has feelings and that would be torturing the animal. But a Furby is interesting because a Furby has a sensor, and when the kid hangs it head upside down, it recognizes that it's not in the right position and it starts to cry. And the Furby cries, and it doesn't cry in one mechanical way. It wails, and it's quiet for a moment, and the distress continues and continues. And you can see in the kid that they're like, oh, I know it doesn't have emotions, but I kind of want to turn it back on. And I think these kinds of questions are more and more important when we live in a society where our work is being done by robots and automation. Many of you might have seen this video where the researcher is shoving the robot, and it kind of makes me feel bad, even though I understand on a very profound level that the robot doesn't have feelings. But then the question is that if a robot is going to make our cappuccinos, if we're going to have a lot of servant robots around us, do we want a society where you can shove the robot? Is that where we want to live in? Finally, we forget that the roots of coding are in poetry and math. The very first programmer in the world was Ada Lovelace, who was the daughter of a poet and a mathematician. Her father was Lord Byron, and she was the first person in the world to understand that computers are not only calculators, that with logic you can represent anything in the world. And that's why we call her the first programmer. And technology itself, it's built on humanity. There is not this binary distinction between people who understand technology and people who don't. The world's first computers were humans. They were people in the Victorian era England who were very good at calculating different sequences of numbers. And I think the last computers in the world will be humans too. And the word technology, it comes from Greek, and it's the tools needed to solve problems or do the job, but it's also the skills and competencies and techniques alongside those tools, very human things that are needed to solve problems. Not only tools, also human things. And we adults forget that a lot of time. But when you ask kids, they remember this side of technology. And I'm going to end with this final little story. So I asked Finnish kids to explain to me, what is technology? What is it used for, and who uses it? And my favorite story comes from this 9-year-old kid who says that technology is electricity that loves. Isn't that beautiful? Technology is electricity that loves. It is used to play. I use it to have a conversation with my mom. We use a WhatsApp application. And then finally, and most importantly, people uses technology. Thank you.